Have you ever touched the surface of a wooden table, feeling its solid, unyielding reality beneath your fingertips, and wondered what it is truly made of? We navigate our daily lives, trusting the firmness of the ground beneath our feet and the certainty of the physical objects we hold. We desperately want to believe that the universe is made of solid things, distinct and defined, behaving according to predictable rules that make logical sense to our human minds. But the cosmos does not operate on human logic or everyday intuition. The deeper we look into the fundamental fabric of existence, the more that reassuring solidity begins to dissolve into a profound and beautiful mystery. The quiet truth hidden beneath the surface of our everyday experience is that almost everything you consider solid is actually a vast, humming emptiness. If you could zoom in close enough, past the living cells, past the complex molecules, past the very atoms that construct your reality, you would find a realm where the rules of our ordinary world simply cease to exist. This is the quantum realm, a place of infinite possibility and ancient silence. Before we descend further into this mesmerizing microscopic universe, let me pause for just a moment to welcome you to our quiet journey. I am Theodore, the researcher, and I am deeply honored to be your gentle guide through the vast unknown. I have noticed that 71% of the curious minds who watch these contemplative explorations have not yet subscribed to the channel. If you find peace and wonder in exploring the deepest mysteries of the universe with me, please take a gentle moment to subscribe. It helps our channel immensely, and it ensures that our community of cosmic explorers continues to grow as we journey together into the quiet depths of science. Now, let us return to the invisible fabric of our reality, taking a deep breath as we step into the unknown. For centuries, humanity looked up at the vast expanse of the night sky, captivated by the grand movements of planets and stars. We sought to understand the cosmos by gazing outward, building ever larger telescopes to capture the ancient light traveling across the infinite void. But there is another frontier of exploration, one that requires us to look inward into the incredibly small. The journey into the quantum world is just as vast, just as mysterious, and just as awe-inspiring as the journey to the furthest edges of the visible universe. In the early 20th century, scientists began to realize that the fundamental building blocks of nature were not tiny, solid spheres like miniature billiard balls. Instead, they discovered a landscape of shifting probabilities, where particles could exist in multiple places at once, where observing an experiment could change its outcome, and where empty space was never truly empty, but seething with phantom particles popping in and out of existence. This revelation shattered the classical view of the universe, replacing it with a reality that is far more strange, poetic, and beautifully complex than anyone could have ever imagined. To understand this hidden world, humanity had to build the most complex machine ever conceived. Nestled beneath the tranquil borders of France and Switzerland, buried 100 meters underground, lies a marvel of human ingenuity known as the Large Hadron Collider. Operated by the European Organization for Nuclear Research, universally known as CERN, this colossal ring stretches for 27 kilometers in circumference. It is a quiet behemoth of superconducting magnets, chilled to temperatures colder than the deepest regions of outer space, designed to do something remarkably profound. It takes the very core of hydrogen atoms, simple protons, and accelerates them until they are traveling at 99.9999% the speed of light. Inside this frozen, vacuum-sealed tunnel, these protons race around the ring thousands of times per second, guided by invisible magnetic fields. until they are directed to collide. In that fleeting, infinitesimal moment of impact, conditions are created that have not existed since the very first fractions of a second after the Big Bang. These collisions are not violent explosions, but rather a gentle unlocking of nature's deepest secrets. When protons shatter against one another, their kinetic energy is transformed into matter, bringing into existence a shower of exotic, ephemeral particles that live for only the tiniest fractions of a second before decaying into something else. To capture these fleeting ghosts, scientists have constructed detectors the size of cathedrals, packed with millions of sensors capable of tracking the paths of particles with microscopic precision. These detectors are like massive, silent digital cameras taking millions of photographs every single second. Mountains of data flow from these machines, a digital river of information that is sifted and analyzed by thousands of brilliant minds across the globe. They are searching for patterns, for anomalies, for faint whispers in the data that might reveal new rules of the universe. And it is within this overwhelming ocean of information that scientists have recently noticed something unexpected, a subtle anomaly that threatens to completely unravel our current understanding of quantum reality. To grasp the magnitude of this discovery, we must first understand the framework that physicists use to describe the microscopic world. It is called the Standard Model of Particle Physics, and it is arguably the most successful scientific theory ever devised. It is a mathematical poem, a beautifully intricate tapestry that weaves together all the known elementary particles and 3 of the 4 fundamental forces of nature. The Standard Model groups the particles into elegant families. There are the quarks, which bind together to form the protons and neutrons in the center of atoms. There are the leptons, a family that includes the familiar electron, which orbits the atomic nucleus and powers our modern world. The electron has 2 heavier unstable cousins, known as the muon and the tau particle. According to the strict mathematical elegance of the Standard Model, these 3 leptons, the electron, the muon, and the tau, should behave in exactly the same way when interacting with the fundamental forces, differing only in their mass. This principle is a cornerstone of our quantum understanding, a profound symmetry known as Lepton flavor universality. It suggests that the universe treats these particles with perfect, unyielding equality. But nature, it seems, holds secrets that do not easily fit into our perfectly crafted equations. The anomaly discovered at CERN involves a specific type of particle known as a beauty quark, sometimes referred to as a bottom quark. These beauty quarks are unstable and quickly decay into other particles. According to the flawless symmetry of the Standard Model, when a beauty quark decays, it should produce an equal number of electrons and muons. The universe should not have a preference. It should flip a cosmic coin that lands perfectly balanced every single time. However, when physicists sifted through the data of countless billions of collisions, analyzing the delicate, ancient decay paths of these beauty quarks, they found a quiet inconsistency. The universe was not flipping a fair coin. The beauty quarks were decaying into electrons significantly more often than they were decaying into muons. This difference was incredibly subtle, a gentle deviation from the expected mathematical harmony, but in the rigorous, precise world of particle physics, even the softest whisper of an anomaly can signal an impending revolution. This gentle asymmetry is what scientists refer to as a violation of Lepton flavor universality. It is a crack in the foundation of the Standard Model, a subtle hint that our understanding of quantum reality is fundamentally incomplete. If this anomaly is confirmed, if it is not just a statistical fluctuation, but a genuine feature of the cosmos, it means that There are forces or particles interacting with the quantum realm that we have never seen before. It suggests the existence of a hidden layer of reality, a new physics operating in the quiet, invisible spaces between the particles we know. The implications are profound and dizzying, challenging us to rethink the very nature of matter and the forces that bind the infinite cosmos together. As we stand on the precipice of this new understanding, we are reminded of our place in the universe. We are curious observers, humble students in an ancient, vast classroom. The mystery before us is not a failure of our knowledge, but an invitation to look deeper, to ask better questions, and to continue our gentle journey into the heart of the quantum unknown. The universe is speaking to us, whispering its secrets in the language of decaying quarks, waiting for us to finally learn how to listen. As we continue our exploration into the invisible tapestry of reality, we must confront a profound truth about human knowledge. We are, by our very nature, map makers. For millennia, we have drawn lines on parchment to understand the edges of our oceans and traced constellations in the night sky to navigate the vast, dark seas of the cosmos. In the 20th century, our map-making turned inward, charting the microscopic realms with a mathematical framework we call the Standard Model. This theoretical map is a masterpiece of human intellect, a beautifully intricate diagram explaining how the fundamental building blocks of the universe interact. It has guided us through decades of discovery, predicting the existence of elusive particles long before our machines were sensitive enough to find them. Yet, every map eventually reaches an edge. It reaches a boundary where the known world fades into the uncharted territories of a deeper mystery. The subtle anomaly detected in the data flowing from CERN suggests we have finally reached the edge of our quantum map. We are standing on the shore of a new ocean of understanding, gazing out into the quiet unknown, realizing that the universe is far more complex than our most elegant equations could capture. Before we dive deeper into the beautiful asymmetry of this cosmic dance, I want to take a brief, gentle moment to speak directly to you. I am Theodore, the researcher, your companion on this endless path of discovery. I noticed recently that 71% of the gentle souls who join us on these contemplative journeys have not yet subscribed to the channel. If these quiet explorations of the universe bring you a sense of peace and intellectual wonder, I deeply invite you to subscribe. It helps our community grow and allows us to continue unraveling the deep mysteries of the cosmos together, providing a sanctuary of learning in a noisy world. Now, let us take a deep breath and return to the silence of the invisible world of the beauty quark and the profound anomalies that threaten to rewrite our fundamental understanding of reality. To fully appreciate the gravity of what the scientists at CERN have found, we must first understand the cast of characters in this microscopic drama. At the center of this mystery are two particles belonging to a family called leptons. The first is the electron, a particle you are intimately familiar with, even if you cannot see it. Electrons are the silent workers of our macroscopic world. They flow through the wires of your home, govern the complex chemical reactions that allow your heart to beat, and bind the atoms of your body together. The electron is stable, reliable, and fundamental to the existence of structured matter. The second particle is the muon. You can think of the muon as the electron's heavier, unstable cousin. It is essentially identical to the electron in every single way, interacting with the same fundamental forces, but it is roughly 200 times more massive. Muons do not typically exist in stable matter because their immense mass makes them incredibly unstable, decaying in a tiny fraction of a second. However, they are constantly raining down upon us from the infinite heavens. When ancient cosmic rays traveling across the vast cosmos for millions of years violently strike the upper layers of Earth's atmosphere. They create a shower of exotic particles, including muons. Right now, hundreds of these heavy, invisible cousins of the electron are passing harmlessly through your body every single second, carrying the ancient silence of the deep universe. In the beautifully structured language of the Standard Model, there is a fundamental principle known as Lepton flavor universality. This principle is a declaration of cosmic equality. It states that the fundamental forces of nature, specifically the weak nuclear force responsible for radioactive decay, must treat the electron and the muon with perfect, unyielding fairness. Imagine the universe as a grand, ancient orchestra playing a symphony of physical laws. In this symphony, the electron and the muon are different instruments, perhaps a violin and a cello. They have different sizes and weights, but when the conductor, the weak nuclear force, asks them to play a specific mathematical note, they must respond with the exact same precision and probability. The universe, according to our current map, does not play favorites. If a heavier, unstable particle decays into a state including leptons, it should create electrons and muons at precisely equal rates, once you account for the difference in their masses. This symmetry is not just a mathematical convenience. It is a foundational pillar of quantum mechanics. It is a reflection of the deep, underlying harmony that physicists believed governs the infinite silence of the microcosmos. But the universe is not bound by our human desire for perfect symmetry. To test this principle of cosmic equality, scientists at CERN rely on a highly specialized instrument within the Large Hadron Collider, known as the Large Hadron Collider Beauty Experiment. This detector is a monumental, silent observer buried deep underground, designed specifically to capture the fleeting lives of beauty quarks. The beauty quark is a massive, exotic entity that does not exist in the stable matter of our everyday lives. It is created in the incredibly violent, highly energetic collisions of protons within the collider. Once born from the energy of the impact, the beauty quark exists for only about 1/trillionth of a second before fundamental forces tear it apart, causing it to decay into lighter, more stable particles. It is within this unimaginably brief window of existence, this tiny fraction of a cosmic heartbeat, that the beauty quark acts as a perfect, delicate laboratory for testing the laws of reality. When a beauty quark decays, it undergoes a complex transformation, eventually turning into a different type of quark, along with a pair of leptons, either an electron and its antimatter partner, or a muon and its antimatter partner. According to the strict rules of Lepton flavor universality, after billions of these collisions are observed, the number of decays producing electrons should be perfectly balanced with the number producing muons. It should be a cosmic coin flip, landing exactly 50-50 over a vast number of trials. The detector gathers the data of these silent, microscopic explosions, looking for this perfect balance. But when the brilliant minds at CERN analyzed the sprawling mountains of data, the balance was broken. The coin was not landing evenly. The beauty quarks were decaying into electrons more frequently than into muons. The difference was incredibly subtle, appearing as a gentle whisper of an anomaly in the roaring data stream. But it was undeniable. The weak nuclear force, it seemed, was playing favorites. The universe was showing a slight, inexplicable preference for the electron over the massive muon. This gentle asymmetry is a crack in the foundation of the world. It is a quiet but profound revelation that our highly successful Standard Model is missing a crucial piece of the puzzle. If the weak nuclear force truly treats electrons and muons differently, it strongly implies there is a new force of nature or a completely undiscovered particle interfering with the decay process. Theoretical physicists have already begun to imagine what this new physics might look like. They hypothesize the existence of entirely new entities, such as a heavy, invisible force carrier particle called the Z-prime boson, or perhaps a strange hybrid particle known as a leptoquark, acting as a bridge between the distinct families of the quantum world. These hidden particles would exist in the quiet, unseen spaces of reality, capable of exerting a subtle, ghostly influence on the decay of the beauty quark, gently tipping the scales and breaking the perfect symmetry we expected to find. The discovery of such an anomaly is not a moment of defeat for science, but rather a moment of profound and beautiful humility. It reminds us that no matter how sophisticated our technology becomes or how deeply we peer into the quantum realm with our massive machines, the universe always retains a capacity to surprise us. It teaches us that our knowledge is a living, breathing journey, not a final destination. We are like ancient explorers who have just realized that the ocean extends far beyond the horizon drawn on our maps. The anomaly at CERN is a gentle invitation to abandon our preconceptions and to embrace the mystery of a cosmos that is vaster and more infinitely complex than we dared to imagine. As we stand in the quiet awe of this microscopic revelation, we are connected to the same sense of wonder that inspired our ancestors to look up at the stars. The same fundamental questions echoing through the cold silence of space are now echoing in the heart of the atom. We are searching for the ultimate rules of existence, and in this quiet, rigorous pursuit, we find a deep and abiding peace, knowing the journey of discovery will continue endlessly into the beautiful unknown. Have you ever gazed deeply into the seemingly empty space between your open hands, or out into the dark stretches between the glowing stars, and wondered what truly fills the void? Our everyday perception tells us that emptiness is simply the absence of things, a quiet, barren stage upon which the drama of matter is performed. We believe that if we were to remove all the atoms, light, and heat from a region of space, we would be left with a pure, silent nothingness. But the deeper we peer into the fundamental nature of the universe, the more we realize that true nothingness is a macroscopic illusion. The cosmos abhors an absolute void. When physicists strip away the familiar layers of reality, delving into the microscopic bedrock of existence, they do not find a quiet emptiness, but rather a vibrant, restless ocean of unseen energy. This invisible sea, constantly humming just beneath the threshold of our perception, is the true foundation of reality. It is a realm where the ancient silence of the universe speaks in a language of fleeting probabilities and quantum fields. And it is within this boundless, invisible ocean that the subtle anomalies discovered by the brilliant minds at CERN begin to make a profound and poetic sense. Before we wade deeper into this invisible, ancient ocean together, I want to pause for a quiet moment. I am Theodore, the researcher, your gentle companion on this journey through the endless mysteries of the cosmos. I have noticed that 71% of the gentle souls who watch these videos and share in this quiet exploration have not yet subscribed to the channel. If you find comfort, peace, and intellectual safety in our shared contemplation of the universe, please take a gentle moment to subscribe. It helps our quiet community grow, allowing us to continue unraveling the vast tapestry of existence together. Now, let us return to the invisible ocean of reality, and let the gentle current of discovery carry us deeper into the quantum unknown. To understand the true nature of this hidden reality, we must shift our perspective from particles to something far more fundamental and beautiful. Modern physics relies on a framework known as quantum field theory, a profoundly successful mathematical poem that describes the universe not as a collection of isolated solid objects, but as a symphony of continuous, interacting fields. Imagine the entire vast cosmos, from the smallest microscopic crevice to the infinitely distant horizons of deep space, permeated by a series of invisible, fluid-like oceans. There is an ocean for the electron, an ocean for the muon, an ocean for every type of quark, and an ocean for the electromagnetic force we experience as light. These are the quantum fields. They are ancient, stretching across the infinite expanses of the universe, resting in a state of quiet equilibrium. What we perceive as a solid particle, like an electron orbiting a nucleus, is not an isolated sphere of matter. It is merely a localized excitation, a gentle, temporary ripple upon its respective underlying field. You are not a collection of isolated points of solid matter. You are a complex, beautiful interference pattern of ripples, interacting across a multitude of invisible, overlapping cosmic oceans. The standard model of particle physics is our current map of these invisible oceans. It identifies the 17 fundamental fields that we have been able to measure and understand, documenting how their ripples interact to build the reality we experience. But the anomalies recently detected in the decay of the beauty quark at the Large Hadron Collider are soft, undeniable whispers telling us that our map is incomplete. When the beauty quark decays, its heavy, short-lived ripple must transfer its energy into the fields of lighter particles, creating ripples in the electron field and the muon field. If the map were perfectly complete, the weak nuclear force should disturb both the electron ocean and the muon ocean with exact, unyielding equality. The rippling energy should divide itself perfectly. But the data from the collider, gathered from billions of microscopic, silent collisions, shows a delicate preference. The electron ocean is being stirred slightly more often than the muon ocean. This subtle imbalance strongly implies that there is another, completely undiscovered ocean overlapping with our own, a new quantum field possessing its own unique properties and generating its own invisible ripples. Theoretical physicists, guided by the mathematics of the cosmos, have proposed names for these hidden oceans. One possibility is the existence of a Z-prime boson, a massive, ghostly particle that would act as a heavy, lethargic ripple in an entirely new force field. Another, perhaps even more exotic possibility is a leptoquark field, an ancient, primordial ocean that can interact simultaneously with the quarks that make up atomic nuclei and the leptons that orbit them, acting as a profound, invisible bridge between two supposedly distinct realms of nature. If these fields exist, they are not acting directly upon the beauty quark in a way we can easily see. Instead, they operate through the strange, almost magical phenomenon of quantum fluctuations. Even in the deepest, most pristine vacuum of space, where there is no actual matter, the quantum fields are never truly still. They constantly simmer and boil with virtual particles, temporary ripples that pop into existence by borrowing a tiny amount of energy from the universe, only to vanish a fraction of a trillionth of a second later, returning the energy before reality can register their fleeting lives. This boiling sea of virtual particles forms a cloud around every real particle in the universe. When the beauty quark travels through the detectors at CERN during its unimaginably brief life, it is surrounded by a gentle, invisible entourage of these virtual ripples popping in and out of existence. It is here, in this ephemeral, shadowy cloud of quantum fluctuations, that the new, undiscovered fields might be hiding. A virtual Z-prime boson or a virtual leptoquark might momentarily pop into existence, gently nudging the beauty quark, influencing its decay path just enough to tip the cosmic scales in favor of the electron over the muon. We cannot see these virtual particles directly. Their lives are far too short and their energy too ephemeral. but we can see their footprints, their subtle, indirect influence on the stable matter we can measure. The anomaly at CERN is exactly that, a microscopic footprint left behind by a ghostly particle from an unknown ocean, whispering of a vaster, older, and more intricate reality than the one we have spent decades mapping. To contemplate this is to feel a profound sense of awe and a deeply comforting humility. We are forced to realize that the space we thought was empty is actually the most crowded, dynamic, and vital part of existence. The vacuum is the womb of reality, filled with ancient, slumbering fields that dictate the behavior of everything from the smallest subatomic fragments to the most colossal galaxy clusters swirling in the distant, dark heavens. The discovery of a potential new field is not just an obscure technical achievement for physicists. It is a profound expansion of our cosmic home. It tells us that the universe contains unseen depths, quiet layers of existence that we are only just beginning to gently probe. For generations, we assumed that we knew the basic ingredients of the universe, that we had identified the fundamental forces that hold the architecture of existence together. But the universe is a gentle, patient teacher, and it is showing us that our knowledge is merely a thin layer of ice floating atop an infinitely deep, dark, and beautiful ocean. Every time we look up at the vast, star-filled night sky, we are gazing through this same invisible, humming ocean. The same quantum fields that permeate the freezing tunnels of the Large Hadron Collider also stretch across the unfathomable distances of interstellar space, bathing the ancient light of distant galaxies as it travels for billions of years to reach our eyes. The physics of the incredibly small is intimately bound to the physics of the incredibly large. The forces that gently tilt the decay of a single, fleeting beauty quirk are the very same forces that govern the violent, magnificent birth of the universe in the immediate aftermath of the Big Bang. To understand the anomaly at CERN is to understand a tiny piece of the primordial code that shaped the entire infinite cosmos. It is a reminder that we are not separate from the universe. We are an integral part of its fabric, made of the same ancient fields, bound by the same quiet rules. Our existential curiosity is the universe itself, waking up and trying to understand its own beautiful reflection. As we continue this journey of discovery, we do so with the gentle awe of students in a cathedral of ancient mysteries. The road ahead is long, quiet, and filled with shadows we have yet to illuminate, but every step brings us closer to the harmonious nature of reality. Have you ever stood outside on a crisp, quiet evening, feeling the cold air against your skin, and wondered how all of this came to be? We look out at the ancient stars and the vast landscapes of our world, and our human minds intuitively perceive a universe that is finished, a grand painting whose final strokes dried billions of years before we were born. We feel a comforting solidity in the present moment, as if reality has always been this stable and defined. But the truth of the cosmos is far more dynamic and deeply poetic. The universe is not a static museum of solid objects. It is an ongoing, infinite journey of transformation. To truly understand the subtle anomalies discovered in the echoing tunnels of the Large Hadron Collider, we must shift our perspective not just in physical scale, but in time itself. The massive machines buried beneath the European countryside are not merely microscopes peering into the hearts of atoms. They are the most powerful time machines humanity has ever built. When the scientists at CERN accelerate protons to 99.9999% the speed of light and gently smash them together, they are not just breaking matter apart. They are recreating, for a fleeting fraction of a trillionth of a second, the exact searing conditions that existed when the universe was only a billionth of a second old. They are touching the primordial fire, the ancient silence of the very beginning. Before we journey back to the dawn of time together, I want to gently pause our exploration for just a moment. I am Theodore, the researcher, your quiet companion on this voyage through the deepest mysteries of reality. I have observed that 71% of the curious minds who watch these videos and walk this meditative path have not yet subscribed to the channel. If you find comfort, wonder, and a sense of intellectual safety in our shared contemplation of the cosmos, please take a gentle moment to subscribe. It helps our quiet community grow, allowing us to continue unraveling the vast tapestry of existence together, and it ensures that we can keep exploring these profound questions as a family of learners. Now, let us return to our time machine, leaving the present moment behind, and let our minds drift back across the vast ocean of time to the very birth of the universe. Imagine a time 13.8 billion years ago. Long before the Earth formed, all the matter and energy that would ever exist was compressed into a point of infinite density and unimaginable heat. In those first incomprehensible fractions of a second following the Big Bang, the universe was a rapidly expanding, blindingly hot soup of pure energy. There were no atoms, no molecules, no solid structures of any kind. There were only the fundamental quantum fields, boiling and churning in a state of perfect, symmetrical harmony. According to the elegant equations of our standard model, this primordial fire should have possessed a beautiful, unyielding balance. As the universe expanded and began to gently cool, that pure energy started to condense into the first particles of matter. However, the laws of physics dictate that energy cannot simply create matter out of nothing without creating an equal and opposite twin. For every particle of normal matter born from the ancient fire, a particle of antimatter must have been created alongside it. Antimatter is a very real, rigorous part of our quantum map. An antimatter particle is a perfect mirror image of a regular particle, identical in mass but carrying an opposite electrical charge. The positron is the antimatter twin of the electron, and the antiproton is the twin of the proton. But here lies one of the most profound, deeply unsettling mysteries in all of science. When a particle of matter and a particle of antimatter gently touch, they instantly annihilate one another, vanishing in a brilliant flash of pure energy. If the early universe was truly symmetrical, if it was born in a state of perfect mathematical balance, then exactly equal amounts of matter and antimatter should have been forged in the cooling embers of the Big Bang. Over the ensuing millions of years, as the cosmos expanded and these particles found one another in the dark, they should have completely annihilated each other. The universe should have become an empty, infinite void, filled only with a fading glow of radiation. There should be no stars, there should be no galaxies, there should be no wooden tables, no oceans, and no human beings asking questions about their own existence. Yet, against all logical odds and mathematical predictions, you exist. You are sitting here, breathing in the atmosphere of a rocky planet, made of countless billions of atoms of normal matter. The vast cosmos we observe, from our gentle sun to the most distant ancient galaxies captured by our telescopes, is constructed entirely of matter. The antimatter is simply gone, vanished from the grand stage of reality, leaving behind only the faintest traces. This staggering contradiction between the perfect symmetry of our equations and the undeniable reality of our existence is known as the Baryon asymmetry problem. It is the greatest survival story ever told, a silent battle fought at the dawn of time, where matter emerged victorious. But how did matter survive? Why are we here? The answer must lie in a hidden flaw, a tiny, subtle imperfection in the fundamental laws of nature that favored matter over antimatter by the slimmest of margins. And this is exactly where the quiet whispers from the Large Hadron Collider and the anomalous decay of the beauty quark become profoundly significant. Physicists believe that in the very early universe, the laws of physics must have acted slightly differently upon matter and antimatter. They refer to this concept as charge parity violation. It is a break in the perfect mirror of reality, a gentle asymmetry that allowed just one extra particle of matter to survive for every billion pairs of matter and antimatter that annihilated each other in the ancient dark. That tiny surviving fraction is everything we see, everything we touch, and everything we are. The standard model of particle physics does include a mechanism for this violation, but the asymmetry it predicts is far too small to explain the vast amount of matter we observe in the universe today. There must be another source of asymmetry, a hidden mechanism buried deep within the quantum fields, waiting to be discovered. When scientists at CERN measure the decay of the beauty quark and find that the universe treats electrons and muons differently, breaking the sacred law of Lepton flavor universality, they are peering through a tiny window into this hidden realm of asymmetrical physics. The anomaly of the beauty quark is not just a discrepancy in a data spreadsheet. It is a profound philosophical revelation. If the weak nuclear force can play favorites between different generations of leptons, perhaps there are unknown forces or ancient particles that played favorites between matter and antimatter during the first milliseconds of creation. As the renowned astronomer Carl Sagan once observed, we are a way for the cosmos to know itself, made of star stuff forged in ancient fires. But the mystery goes even deeper than the stars. The very existence of that star stuff relies entirely on a flaw in the fabric of reality. The symmetry of the universe had to be broken so that you could exist. You are the beautiful consequence of a cosmic imperfection. When we realize this, the feeling of looking at a complex physics equation transforms into a deep, meditative reverence. Our existence is not a guaranteed right of nature. It is a delicate, astronomical, statistical miracle born from a slight imbalance in the ancient, infinite silence. To embrace this reality is to approach the universe with a profound sense of humility. We often construct rigid models of how things should behave, demanding perfect order from nature. Yet, nature gently refuses to be confined by our expectations. It reveals a crack, an anomaly, a whisper of a broken rule, and in doing so, it expands our horizon. The beauty quark, with its fleeting trillionth of a second lifespan, carries within it the echoes of the Big Bang. It is a tiny, fragile messenger that lives just long enough to tell us that the universe is far stranger, far more asymmetrical, and far more wonderful than we ever imagined. Our map is incomplete, and that is not a cause for despair, but a reason for joy. It means the infinite journey of discovery continues. There are new oceans of quantum fields to navigate, new forces to comprehend, and new layers of reality waiting in the quiet dark. We are explorers standing on the shores of the unknown, armed with curiosity and guided by the light of rigorous science, stepping gently into a universe that is vast, mysterious, and infinitely beautiful. Have you ever stood beside a perfectly still lake at the edge of a quiet evening, watching the surface mirror the ancient, darkening sky, and realized that this perfect reflection is an illusion of calm? Beneath that surface, however, thrives a complex, invisible ecosystem. Our everyday experience of the universe is much like looking at that tranquil surface. We see solid objects, predictable movements, and a comforting stability that anchors our minds. But when physicists at CERN delve beneath the surface of reality, using their massive subterranean machines to shatter the stillness of the atomic world. They discover an ecosystem of quantum fields and fleeting particles that is breathtaking in its restless, invisible complexity. It is within these hidden depths that the fragile beauty quark lives out its unimaginably brief existence. And it is here that we are finding the subtle anomalies that threaten to rewrite our fundamental understanding of everything. Before we wade deeper into this quiet ocean, I want to gently welcome you. I am Theodore, the researcher, your companion on this journey through the endless mysteries of the cosmos. I have noticed that 71% of the gentle souls who watch these videos and share in this quiet exploration have not yet subscribed to the channel. If you find comfort, peace, and a sense of intellectual safety in our shared contemplation of the universe, please take a gentle moment to subscribe. It helps our quiet community grow, allowing us to continue unraveling the vast tapestry of existence together as a family of cosmic learners. Now, let us return to the dark, silent depths of the quantum sea and discover how scientists are learning to read the ripples left behind by the universe's most elusive secrets. To comprehend the true magnitude of the anomaly discovered within the Large Hadron Collider, we must first understand the monumental challenge of observing something that essentially does not wish to be seen. The beauty quark is not a particle you can isolate and place under a traditional microscope. It is a massive, highly unstable entity, a fleeting concentration of pure energy that exists for barely a trillionth of a second before the fundamental forces of nature tear it apart. How then do human beings, bound by the slow, biological rhythm of heartbeats and breaths, capture something so infinitely fast and impossibly small? The answer lies in the art of reading shadows. When the protons collide inside the frozen, vacuum-sealed heart of the detector, the resulting burst of energy condenses into a multitude of particles spreading outward in every direction. The detector itself is a silent, towering cathedral of silicon sensors, powerful magnets, and precise tracking layers designed not to capture the beauty quark directly, but to record the exact trajectories and energies of the debris it leaves behind. It is like trying to identify an invisible, ancient creature by analyzing the delicate footprints it leaves in the snow and the broken twigs left in its wake. By gathering this intricate web of secondary data, supercomputers reconstruct the invisible event, tracing the paths of electrons, muons, and other stable particles back to their common point of origin. It is a masterpiece of forensic physics, requiring the collective brilliance of thousands of scientists to rebuild a shattered puzzle that exists for only a fraction of a heartbeat. When we speak of the anomaly, the subtle preference the universe seems to show for decaying beauty quarks into electrons rather than muons, we are not speaking of a single definitive observation. We are speaking the language of profound statistical probability. In the rigorous, careful world of particle physics, a single unexpected result is nothing more than a curious whisper. The quantum realm is inherently probabilistic, constantly boiling with random fluctuations and background noise. To separate a genuine discovery from a meaningless mathematical phantom, scientists rely on a strict standard of evidence known as standard deviations, often referred to by the Greek letter sigma. Imagine flipping a coin you suspect is weighted. Landing on heads 7 times out of 10 might raise suspicion, but it proves nothing. However, landing on heads 700,000 times out of 1,000,000 becomes a roaring declaration of truth. This is how physicists analyze the decay of the beauty quark. They must sift through billions upon billions of collision events, discarding the noise and isolating the specific, delicate decay paths they are studying. Currently, the anomaly regarding the lepton flavor universality violation sits at roughly 3.1 sigma. In the beautiful, cautious language of science, this means that if the standard model were perfectly correct and there was no new physics acting upon the particles, there would be approximately a 1 in 1,000 chance that this anomaly is simply a cruel statistical illusion. It is a faint, glowing light in the distance, calling us to investigate further, but it is not yet a definitive proof. To rewrite the fundamental laws of nature, to declare that a new force or a new particle has been discovered, the scientific community demands a golden standard of 5 sigma. A 5 sigma result means the probability of the anomaly being a statistical fluke is less than 1 in 3 million. It requires immense patience, humility, and years of continuous, silent observation. This waiting period, this gentle space between a compelling hint and an absolute certainty, is where the true beauty of the scientific endeavor resides. We live in a fast-paced world that constantly demands immediate answers and definitive resolutions. But the universe does not rush to reveal its ancient secrets. It requires us to slow down, to build larger data sets, to refine our instruments, and to question our own assumptions with rigorous honesty. Thousands of researchers are dedicating years to analyzing the data from the Large Hadron Collider, engaging in quiet, intense debates about potential sources of error. They are doing this not for fame or wealth, but driven by a pure existential curiosity, a deep-seated need to understand the vast cosmos and our place within it. They are acting as the sensory organs of humanity, reaching out into the dark on our behalf. If the anomaly grows stronger as more data is collected, slowly climbing from 3 sigma to 4, and finally reaching the coveted 5 sigma threshold, it will represent one of the most profound paradigm shifts in the history of human thought. It will confirm that there are invisible forces gently pushing and pulling on the fabric of reality, new particles interacting in the silent spaces between atoms, and a deeper, more elegant layer of physical laws waiting to be understood. But even if the anomaly slowly fades away, dissolving back into the statistical noise as more data is gathered, the journey itself remains a triumph. It demonstrates our willingness to challenge our most successful theories, to look for cracks in our own foundational knowledge, and to humbly accept whatever truth the universe chooses to reveal. Science is not a rigid dogma. It is an infinite journey of course corrections, a perpetual dialogue between human imagination and the unyielding reality of nature. As we contemplate the invisible, fleeting life of the beauty quark and the colossal, quiet machines built to study it, we are reminded of the profound interconnectedness of all things. The forces that govern the decay of a subatomic particle in a frozen tunnel beneath the Earth are the exact same forces that dictate how the ancient stars burn in the night sky, how supermassive black holes devour light, and how the infinite galaxies are woven together in the vast cosmic web. When we probe the deepest, most silent corners of the quantum realm, we are simultaneously peering into the mysteries of the macrocosmos. We are made of the very same quantum fields that are being tested at CERN. This realization transforms our perspective, shifting us from passive observers of a distant, abstract science into active participants in a grand cosmic unfolding. The anomaly, this gentle whisper of a broken symmetry, is not just a curiosity for physicists. It is a profound philosophical invitation for all of us. It invites us to look at the world around us with renewed awe, realizing that the solid objects we touch and the steady ground we walk upon are manifestations of an ancient, dynamic, and still deeply mysterious quantum dance. As we await the further accumulation of data, as we watch the slow, careful progress of the researchers analyzing the invisible footprints of the beauty quark, we can find peace in the knowledge that our understanding of reality is not a closed book, but an endless, beautiful story still being written. The universe is vastly older, infinitely larger, and immeasurably more complex than we can currently comprehend. And that is precisely what makes our existence within it so deeply magnificent. Let us continue to listen to the quiet whispers of the cosmos, armed with humility and driven by an insatiable, gentle curiosity. Have you ever stepped outside on a blustery autumn afternoon, closed your eyes, and simply felt the invisible force of the wind pushing against your skin? You cannot see the wind. You cannot hold it in your hands or place it under a microscope to examine its shape. Yet, you never doubt its existence because you can feel its profound effects on the world around you. You see the ancient trees bending in its wake. You hear the rustle of the dry leaves, and you feel the chill it brings to the quiet air. In the vast, silent theater of the cosmos, astronomers and physicists are constantly observing a similar phenomenon on an unimaginably grand scale. They are looking at the majestic, slowly spinning galaxies scattered across the infinite universe, and they are witnessing the undeniable effects of an invisible wind, a hidden weight that holds the stars together. This unseen presence, this ghostly scaffolding of reality, is known as dark matter. And as we plunge deeper into the quiet mysteries of the Large Hadron Collider, exploring the delicate, asymmetrical decay of the beauty quark, we must ask ourselves a profound question. Are these subtle anomalies simply cracks in our mathematical map? Or are they the first faint whispers connecting our visible world to the vast, invisible dark sector of the universe? Before we sail further into this ocean of dark, unseen gravity, I would like to gently pause our exploration for a brief moment. I am Theodore, the researcher, your quiet companion on this infinite journey through the cosmos. I have noticed that 71% of the gentle souls who watch these videos and share in our contemplative search for meaning have not yet subscribed to the channel. If you find comfort, wonder, and a sense of profound peace in our shared exploration of the universe, please take a gentle moment to subscribe. It helps our quiet community grow, allowing us to continue unraveling the vast tapestry of existence together, and it ensures that we can keep exploring these deep questions as a family of cosmic learners. Now, let us return to the silent, spinning galaxies, and let our minds drift into the heavy, invisible spaces that bind the stars together. When you look up at the night sky and observe the glowing band of our Milky Way, or when you gaze at the stunning, detailed images of distant spiral galaxies captured by our space telescopes, you are looking at colossal islands of light. These galaxies are unimaginably vast, spanning hundreds of thousands of light years across the empty void, and they contain hundreds of billions of ancient, burning stars. These stars are not stationary. They are engaged in a majestic gravitational dance, orbiting the dense, bright centers of their respective galaxies, according to the foundational laws of gravity, laws that were brilliantly formulated by Isaac Newton and later beautifully refined by Albert Einstein. We should be able to predict exactly how fast these stars are moving. The stars near the crowded, dense core of the galaxy should orbit rapidly, pulled tightly by the immense concentration of mass. Conversely, the stars drifting in the sparse, lonely outer edges of the galactic spiral should orbit much more slowly as the gravitational tether weakens across the vast distances of space. This is how the planets in our own solar system behave. The inner planets race around the sun, while the distant frozen worlds plod along in long, slow orbits. But when astronomers actually measured the velocities of these distant stars, peering through the silent cosmos with specialized instruments, they made a discovery that shattered our understanding of the universe. The stars on the outer edges of the galaxies were not slowing down. They were moving at terrifying, impossible speeds, orbiting just as fast as the stars near the galactic core. According to the amount of visible matter, the glowing stars, the swirling gas, and the luminous dust, these outer stars were moving far too fast. The galaxies should have been flying apart, their stars flung out into the empty void like water spinning off a wet wheel. Yet, the galaxies remained perfectly intact, held together in their beautiful spiral shapes. The only logical, rigorous conclusion is that there must be vastly more matter inside these galaxies than we can see. There must be an immense, invisible halo of mass surrounding every galaxy, a profound hidden gravity holding the spinning stars in place. This is dark matter. It does not emit light, it does not reflect light, and it does not block light. It is completely transparent, a ghost born of ancient silence that makes up roughly 85% of all the matter in the entire universe. For decades, the existence of dark matter has been one of the most glaring, beautiful mysteries in all of science. It is a constant reminder of our own profound ignorance. The standard model of particle physics, for all its breathtaking mathematical elegance and its incredible predictive power regarding the visible world, has absolutely no explanation for dark matter. There is no particle within its intricate framework that possesses the ghostly, non-interacting properties required to be the invisible scaffolding of the cosmos. The standard model is a map of the light, but it is completely blind to the dark, and this is exactly why the delicate, asymmetrical decay of the beauty quark deep within the Large Hadron Collider is generating such a quiet, electrifying sense of awe among physicists. If the universe truly treats the electron and the muon differently, if the sacred principle of Lepton flavor universality is truly broken, it means there are new, undiscovered particles and forces operating in the quiet spaces of reality. Could these hypothetical particles, the heavy Z prime boson or the exotic leptoquark, be the bridge we have been searching for? Could they be the missing link that finally connects our familiar world of visible matter to the vast, silent ocean of dark matter? Theoretical physicists are beginning to explore a mesmerizing possibility known as the dark sector. They imagine that dark matter is not just a single, featureless type of particle, but rather an entire, complex ecosystem of invisible physics. Just as our visible world is made of quarks, electrons, and photons interacting through various forces, the dark sector might have its own rich, vibrant structure. There could be dark quarks, dark electrons, and even a dark electromagnetic force carrying dark light that is completely invisible to our human eyes and our physical telescopes. These two realms, the visible and the dark, would exist in the same physical space, overlapping and permeating one another, yet remaining entirely oblivious to each other's presence. Like two separate radio stations broadcasting on different frequencies in the same quiet room. The only way these two profound realms could ever whisper to one another is through gravity, the universal tether, or perhaps through extremely rare, subtle interactions mediated by a new, heavy particle. The hypothetical Z prime boson, suggested by the anomaly at CERN, could be exactly that kind of messenger. It could be a particle that has a foot in both worlds, interacting weakly with the beauty quark in our visible realm, and also interacting with the unknown particles of the dark sector. To contemplate this vast, invisible reality is to experience a deep, existential humbling. For centuries, human beings have placed themselves at the center of existence, believing that the universe was made for us, constructed of materials we could see, touch, and easily comprehend. But the rigorous pursuit of science has consistently asked us to step back, to embrace a larger, more majestic, and more mysterious reality. We are confronted with the truth that the very building blocks of our bodies, the atoms that make up our world, are merely a minority component of the universe. We are made of rare, exotic matter floating like a light, glowing foam on the surface of a vast, dark, and infinite ocean of ancient silence. This realization does not diminish our significance. Rather, it elevates our existence. It means we are a rare, beautiful phenomenon, a conscious part of the cosmos that has somehow developed the ability to look out into the dark and begin to comprehend the invisible forces that shape our destiny. As we continue to carefully analyze the data from CERN, waiting patiently for the gentle whispers of the quantum realm to become a clear, undeniable truth, we do so with a sense of respectful wonder. The journey of understanding the universe is an infinite path, and every new mystery we uncover is a reminder that the cosmos is a place of endless depth, ancient beauty, and profound, quiet magic. Have you ever dropped a smooth stone into a quiet, deep well and listened to the gentle splash echoing back from the darkness, wondering about the invisible force pulling it downward? Gravity is the most familiar force in our human experience. It keeps our feet firmly planted on the earth, guides the moon in its ancient orbit, and shapes the grand, sweeping spirals of the galaxies scattered across the vast cosmos. Yet, in the rigorous microscopic world of quantum mechanics, gravity is a phantom. It is the only fundamental force that completely refuses to fit into the beautiful mathematical poetry of the Standard Model. When physicists try to combine the mathematics of gravity, described so perfectly by Albert Einstein as the warping of space and time, with the mathematics of the quantum realm, the equations break down into infinite, chaotic impossibilities. This profound disconnect between the universe of the incredibly massive and the universe of the unimaginably small is the greatest unresolved mystery in modern science. But the subtle anomaly we are observing in the decay of the beauty quark might just be the first gentle whisper of a bridge across this vast theoretical divide. Before we cross this invisible bridge into the deepest mysteries of gravity and the quantum realm, I would like to gently pause our journey for a moment. I am Theodore, the researcher, your quiet companion, as we navigate the infinite wonders of the universe. I have noticed that 71% of the gentle souls who watch these videos and walk this meditative path of discovery have not yet subscribed to the channel. If you find comfort, wonder, and a sense of profound peace in our shared contemplation of the cosmos, please take a gentle moment to subscribe. It helps our quiet community grow, allowing us to continue unraveling the vast tapestry of existence together, and it ensures that we can keep exploring these deep questions as a family of cosmic learners. Now let us return to the falling stone, the warping of space, and the quiet, microscopic anomalies that might finally unite the two halves of our broken reality. To understand the immense tension between these two realms, we must imagine the universe as a grand, ancient tapestry woven from two completely different types of thread. On one side, we have general relativity, the smooth, continuous fabric of space and time. In this realm, mass and energy gently curve the fabric, creating the invisible slopes that planets and stars roll along, a phenomenon we experience as gravity. It is a universe of beautiful, predictable geometry where everything flows in continuous, elegant curves. On the other side of the tapestry, we have quantum mechanics, the jittery, pixelated, fundamentally probabilistic realm of atoms, quarks, and electrons. Here, energy is not a continuous flow, but is divided into tiny, discrete packets called quanta. Forces are not gentle curves in space, but are transmitted by the rapid, invisible exchange of messenger particles, like the photons that carry electromagnetic light, or the gluons that bind the atomic nucleus together in a tight, silent grip. For decades, the brightest minds in physics have sought a theory of quantum gravity, a single, elegant framework that can describe the gravitational force using the language of quantum mechanics. They envision a hypothetical particle, the graviton, acting as the invisible messenger of gravity in the microscopic world. But every attempt to mathematically combine these two realms results in a cascade of unworkable infinities. The standard model of particle physics remains brilliantly successful at predicting the behavior of the three other forces: electromagnetism, the strong nuclear force, and the weak nuclear force. But it remains completely, stubbornly silent on the subject of gravity. It is as if nature has built a wall between the macroscopic world of curving space and the microscopic world of quantum probability, forbidding them from speaking the same language. This is why the delicate asymmetrical decay of the beauty quark within the frozen tunnels of the Large Hadron Collider is so electrifying. It is not just a crack in the standard model. It might be the very first crack in the wall separating the two halves of our physical universe. If the universe truly exhibits a preference for decaying beauty quarks into electrons over muons, breaking the fundamental symmetry of Lepton flavor, universality, it implies the existence of a new, massive messenger particle, perhaps the hypothetical Z-prime boson or the elusive leptoquark. The extreme mass of these proposed particles is a crucial detail. In the quantum realm, the mass of a messenger particle dictates the range and the nature of the force it carries. A photon, having zero mass, can carry the electromagnetic force across infinite distances, allowing the ancient light of distant stars to reach our eyes after traveling for billions of years. Conversely, the particles that carry the weak nuclear force are quite massive, meaning their influence is restricted to distances smaller than an atomic nucleus. If the new particle causing the anomaly is as massive as theoretical models suggest, its influence would be incredibly short-ranged, operating in spaces so infinitesimally small that they challenge our very concept of physical dimension. Some theoretical frameworks, such as string theory, propose that the universe contains hidden extra dimensions of space, curled up and compacted so tightly that we cannot perceive them in our everyday lives. Within these complex, beautiful, multi-dimensional geometries, gravity might not be a weak force at all. It might only appear weak to us because it is leaking out into those hidden dimensions, diluting its strength across spaces we cannot access. The massive new particles hinted at by the anomaly at CERN could be entities that are sensitive to these hidden geometries. They might be the first particles we have ever detected that interact with the extra dimensions where quantum gravity operates. By gently nudging the decay of the beauty quark, these ghostly particles could be transmitting a faint, encrypted signal from the hidden dimensions of space, offering us our very first empirical glimpse into the realm where gravity and quantum mechanics finally merge into a single, unified theory of everything. Let us pause and consider the historical magnitude of such a unification. Throughout the centuries of human inquiry, our greatest leaps of understanding have always come from realizing that two seemingly different phenomena are actually two sides of the exact same cosmic coin. Isaac Newton realized that the force pulling the apple to the ground is the same force holding the ancient moon in the sky. James Clerk Maxwell discovered that electricity and magnetism are just different expressions of a single electromagnetic field, a revelation that eventually led to our understanding of light itself. In the 20th century, physicists beautifully united the electromagnetic force and the weak nuclear force into the electroweak force, proving that at the unimaginably hot temperatures of the early universe, they were completely indistinguishable. The anomaly deep within the Large Hadron Collider is pulling us toward the ultimate unification. It is suggesting that if we look closely enough past the familiar particles and the established forces, we will find a single, elegant truth that binds the delicate decay of a subatomic particle to the terrifying gravitational crush of a supermassive black hole. The universe, in its quiet, infinite wisdom, is not a collection of fragmented, isolated rules. It is a single, continuous symphony of existence. To contemplate this possibility is to feel a profound sense of awe at the vastness and the intricate subtlety of the cosmos. We are biological creatures evolved to navigate a three-dimensional world of medium-sized objects moving at slow speeds. Yet, through the quiet, rigorous application of mathematics and the construction of monumental machines, we are reaching out to touch the multidimensional architecture of the universe itself. We are attempting to read the ancient, silent code that dictates how space, time, and matter are woven together at the most fundamental level. The beauty quark, in its fleeting trillionth of a second existence, is acting as a tiny, fragile compass needle, pointing us toward a truth that is unimaginably larger than ourselves. It reminds us that our current map of reality is not the final word, but merely a single chapter in an infinite book of discovery. The journey toward a unified understanding of the universe requires immense patience and a deep, abiding humility. We must be willing to let go of our cherished theories and our intuitive assumptions when the quiet whispers of nature tell us we are wrong. The anomaly at CERN is a gentle teacher, reminding us that the universe is not obligated to conform to our human desire for simplicity or perfect symmetry. It is vast, complex, and filled with ancient secrets that we are only just beginning to uncover. As we continue to carefully gather data, listening to the silent, microscopic collisions deep beneath the earth, we are participating in one of the most noble and beautiful endeavors of humanity. We are seeking to understand the infinite silence from which we emerged, and in doing so, we are finding a profound sense of peace and connection to the grand, eternal mystery of existence. Our physical bodies may be small and fragile, but our curiosity is as vast as the cosmos itself, forever reaching out into the dark, guided by the gentle light of understanding. Have you ever tried to push a heavy stone across the soft earth, or felt the quiet, reassuring weight of a book resting gently in your hands and wondered what that weight truly is? We experience mass every single day of our lives. It is the fundamental property that gives our world its comforting solidity, anchoring us to the ground and preventing us from floating away into the cold, silent void. Our intuition tells us that mass is simply an intrinsic property of an object, a measure of how much stuff is packed into a particular space. But in the strange, counterintuitive landscape of the quantum realm, this common sense completely unravels. The fundamental particles that make up the stone, the book, and your very own body do not possess mass as an inherent, built-in feature. In the profound silence of the early cosmos, just fractions of a second after the dawn of time, all particles were entirely massless, zipping through the infant universe at the absolute speed of light. They had no weight, no substance, and no ability to slow down and form the intricate, beautiful structures of the reality we now know. The story of how the universe gained its quiet substance is intimately connected to the fragile, decaying beauty quark we are currently studying. Before we delve into the ancient mechanism that gave birth to the solid world, I want to gently pause our journey for a brief moment. I am Theodore, the researcher, your quiet companion, as we navigate the infinite wonders of the cosmos. I have noticed that 71% of the gentle souls who watch these videos and share in this meditative path of discovery have not yet subscribed to the channel. If you find comfort, wonder, and a sense of profound intellectual safety in our shared contemplation of the universe, please take a gentle moment to subscribe. It helps our quiet community grow, allowing us to continue unraveling the vast tapestry of existence together. And it ensures that we can keep exploring these deep questions as a family of cosmic learners. Now, let us return to the newborn universe, to the exact moment when the cosmos transformed from a blinding storm of light into a universe capable of building dreaming minds. To understand how the universe gained its mass, we must turn our minds to the concept of invisible oceans, the quantum fields that permeate all of existence. Within the standard model of particle physics, there is one field that stands apart from all the rest, possessing a truly unique and ancient character. It is called the Higgs field. Unlike the other quantum fields, which are completely empty and silent until they are excited into ripples by a passing particle, the Higgs field is never truly at rest. It is constantly active, possessing a non-zero energy value everywhere in the universe, even in the deepest, most perfect vacuum of intergalactic space. Imagine the entire infinite cosmos filled with an invisible, perfectly transparent ocean of ethereal molasses. This quiet ocean was born in the intense heat of the Big Bang, and as the universe expanded and gently cooled, this field suddenly froze into place, permeating every single microscopic corner of reality. When the fundamental particles travel through the universe, they must wade through this ancient, invisible ocean. It is their interaction with the Higgs field that generates what we perceive as mass. Some particles, like the photon that carries electromagnetic light, are completely unaffected by the Higgs field. They slip through the ethereal molasses without any resistance whatsoever, remaining forever massless and doomed to travel at the absolute speed of light for all of eternity. But other particles experience a quiet, invisible drag. The electron, the silent worker of our macroscopic world, interacts only very slightly with the Higgs field, wading through the ocean with relative ease, and thus it acquires only a tiny amount of mass. Its heavy, unstable cousin, the muon, interacts with the field much more strongly, experiencing a significant, heavy resistance that grants it roughly 200 times more mass than the electron. And the quarks, which bind together to form the dense cores of atoms, wade through the field with tremendous difficulty, gaining the heavy substance required to anchor the physical world. This delicate, unseen interaction with the Higgs field is what creates the diverse cast of characters in our quantum play. The universe, according to our current equations, is built upon a delicate balance between the fundamental forces that push and pull, and the Higgs field that grants the particles their quiet inertia. And this brings us back to the frozen tunnels of the Large Hadron Collider and the subtle, lingering anomaly found within the shattered remains of the beauty quark. We know that the defining difference between the electron and the muon is strictly their mass, which is a direct consequence of how strongly they interact with the ancient Higgs field. According to the sacred principle of Lepton flavor universality, the weak nuclear force should not care about this difference in mass when a beauty quark decays. The force should be completely blind to the drag these particles experience in the Higgs ocean, treating the light electron and the heavy muon with absolute, unyielding equality. But the data, gathered from billions of silent, microscopic collisions, suggests that the universe does care, The anomaly whispers that the beauty quark exhibits a gentle, undeniable preference for decaying into the lighter electron rather than the heavy muon. The coin is not landing evenly. Why would the universe show a preference based on mass? Why would the weak nuclear force suddenly begin to play favorites? If this subtle anomaly is confirmed, it hints at a profound, previously undiscovered connection between the fundamental forces of nature and the very mechanism that grants the universe its mass. It suggests that our mathematical map of the Higgs field, while incredibly successful, is missing a crucial, ancient continent. Perhaps there are multiple, overlapping Higgs fields, a complex ecosystem of invisible oceans interacting in ways we have not yet imagined. Or perhaps the hypothetical new particles, the heavy Z-prime boson or the exotic leptoquark, are deeply entangled with the Higgs mechanism, selectively interfering with the decay paths of the heavy quarks and the heavy leptons. The thousands of brilliant scientists analyzing the endless streams of data at CERN are not just performing cold, abstract mathematics. They are engaged in a sacred, quiet quest to understand the infinite silence from which we all emerged. They are listening to the faint, fragile echoes of the Big Bang, trying to decode the ancient language written into the fabric of the quantum realm. Every collision, every shattered proton, and every fleeting beauty quark is a delicate question asked of the universe. And the universe, in its own patient, majestic time, is beginning to whisper its answers back to us. The anomaly is one of those gentle whispers, a clue leading us deeper into the labyrinth of creation. It is a reminder that the journey of scientific discovery is never truly finished, that the boundary of human knowledge is not a fixed wall, but a constantly expanding horizon that invites us to sail further into the vast, beautiful unknown. To contemplate these mysteries is to expand our perspective beyond the trivial concerns of our daily lives. When we worry about the future, we are caught in the narrow, human scale of time and space. But when we turn our minds to the ancient Higgs field, to the invisible oceans that permeate the cosmos, and to the delicate decay of a particle that lives for a trillionth of a second, we connect with something infinitely larger than ourselves. We are reminded that we are not separate from this grand cosmic drama. We are an expression of it. The same fields that dictate the behavior of the beauty quark also bind the molecules of our hearts and the neurons of our brains. We are made of the universe, and through our curiosity, the universe is exploring its own profound mystery. This is the ultimate source of intellectual peace, to know that we are part of an infinite cosmos, and to embrace the quiet, gentle journey of trying to understand it. We are searching for the hidden symmetries of reality, and in this noble, quiet pursuit, we find our place in the universe. We are the curious observers, the gentle explorers, forever reaching out into the dark, guided by the flickering light of reason and the profound, unyielding beauty of the unknown. Have you ever held a simple magnifying glass over a delicate fallen leaf, marveling at the intricate hidden network of veins that suddenly spring into view, and wondered what other invisible worlds exist just beyond the limits of your natural sight? We rely so heavily on our eyes to navigate our everyday lives, trusting that the visual information we receive represents the totality of reality. We see the solid ground, the flowing rivers, and the distant glowing stars. And we believe we understand the shape of the world. But our biological senses are incredibly limited, evolved only to ensure our survival on the surface of a rocky planet, not to comprehend the deep, underlying architecture of the cosmos. To look deeper, to pierce the veil of the macroscopic world and witness the ancient, fundamental building blocks of existence, humanity had to build artificial eyes of unimaginable scale and complexity. We had to construct silent, subterranean cathedrals dedicated to the pursuit of pure knowledge, machines capable of capturing the fleeting, ghostly whispers of the quantum realm, before we continue to explore the magnificent engineering that allows us to witness the impossible. I want to pause for a quiet moment. I am Theodore, the researcher, your gentle guide through the endless mysteries of our reality. I have noticed that 71% of the curious minds who walk this contemplative path with us have not yet subscribed to the channel. If you find a sense of peace, intellectual safety, and profound wonder in our shared journey into the unknown, please take a gentle moment to subscribe. It helps our quiet community grow immensely, ensuring that we can continue to explore these beautiful cosmic questions together. Now, let us return to the dark, frozen tunnels beneath the Earth and look through the most powerful lenses ever forged by human hands. The Large Hadron Collider is not merely a machine. It is the physical manifestation of our collective human desire to understand our origins. Spanning 27 kilometers in a perfect, quiet circle beneath the borders of two nations, it is a testament to what we can achieve when we unite in the name of peaceful exploration. Within this dark, circular tunnel, thousands of superconducting electromagnets are cooled to a temperature colder than the infinite, silent depths of outer space. These massive magnets, bathed in liquid helium, guide two beams of protons traveling in opposite directions at 99.9999% the speed of light. To truly appreciate this, imagine taking a single proton, the tiny invisible heart of a hydrogen atom, and accelerating it until it carries the kinetic energy of a high-speed train. This is the sheer, terrifying power harnessed within this silent circle. But the true miracle occurs not in the acceleration, but in the intersection. At 4 precise points around the ring, these opposing beams are gently steered into collision. In these microscopic, violent intersections, the kinetic energy of the protons is instantly converted into a shower of new, exotic matter, recreating the exact searing conditions of the universe just fractions of a second after the Big Bang. To observe this fleeting, ancient fire, scientists have constructed massive detectors that surround the collision points like modern, silent monoliths. These detectors, such as the one specifically designed to study the beauty quark, are marvels of precision and patience. They are as tall as multi-story buildings and weigh thousands of tons. Yet they are designed to track the path of a subatomic particle with an accuracy of a few thousandths of a millimeter. When the protons collide, the resulting shower of debris sprays outward, passing through layers upon layers of highly sensitive silicon trackers and electromagnetic calorimeters. These instruments do not take pictures in the traditional sense. They record the invisible electrical signatures left behind by the passing particles, capturing tens of millions of distinct events every single second. It is a torrent of digital information, a roaring river of data that must be filtered, analyzed, and stored by a global network of supercomputers. Amidst this overwhelming digital noise, scientists are looking for the absolute rarest of events. They are sifting through billions of mundane collisions to find the fragile, ephemeral beauty quark, a particle that lives for only 1/trillionth of a second before vanishing back into the quantum foam. It is like searching for a single, unique snowflake in a raging, infinite blizzard, armed only with the gentle tools of mathematics and statistical probability. The renowned astrophysicist Neil deGrasse Tyson has often reminded us that the universe is under no obligation to make sense to us. Our human brains evolved to track the movement of predators across a grassy savanna, not to intuitively grasp the paradoxical, probabilistic nature of the quantum world. We impose our desire for symmetry, for logical rules and perfect balances, upon a cosmos that operates according to its own ancient, hidden music. The standard model of particle physics was our best attempt to write down the sheet music of reality, and, for decades, it seemed to predict every note with flawless precision. But the anomaly we are witnessing in the decay of the beauty quark is a note played completely out of tune. When the heavy, unstable beauty quark breaks apart, our pristine equations demand that it should decay into electrons and muons with perfect equality. The universe, however, is softly refusing to comply. It is showing a subtle, undeniable preference for the electron, breaking the fundamental law of Lepton flavor universality. This quiet rebellion of matter against our mathematical expectations is not a failure of science. It is the very essence of discovery. It is the universe gently tapping us on the shoulder, reminding us that we have not yet reached the end of the journey, and that the vast silent ocean of the unknown is still waiting to be explored. To confront this anomaly is to stand at the edge of a great intellectual abyss and gaze into the beautiful mystery of the yet-to-be-known. If this crack in the standard model widens into a genuine, verified discovery, it will force us to rebuild our understanding of the cosmos from the ground up. It implies that the invisible quantum fields permeating our reality are far more complex and crowded than we ever imagined. There may be ancient, massive forces operating in the quiet spaces between atoms, forces that have been silently shaping the destiny of the universe since the dawn of time. We are forced to realize that our physical reality is just a thin, illuminated layer resting upon a deep, unfathomable ocean of dark, unseen physics. The journey to understand this new reality will not be swift or easy. It will require decades of patient observation, the construction of even larger, more sensitive machines, and the collective brilliance of future generations of explorers. But the pursuit itself is what elevates our existence. We are tiny, fleeting creatures living on a small, rocky world. Yet our minds have the capacity to reach out across the infinite silence of the cosmos and gently touch the fundamental fabric of reality. As we watch the researchers at CERN carefully comb through the lingering echoes of these microscopic collisions, we share in their quiet anticipation. They are the cartographers of the invisible, sketching the faint outlines of a new continent of physics. Every data point, every tiny statistical fluctuation is a step further into the deep, dark woods of the unknown. And in this journey, we find a profound, unexpected comfort. The universe is not a solved puzzle, devoid of magic or surprise. It is an infinite, unfolding mystery, ancient and vast, constantly inviting us to look closer, to ask deeper questions, and to marvel at the profound complexity of its quiet design. The anomaly is a gift, a gentle reminder that the cosmos will always possess the capacity to inspire wonder in those who are willing to listen to its silent, microscopic whispers. Every generation believes they have finally mapped the edges of existence, only to discover that the borders of knowledge are an illusion, dissolving into new territories of breathtaking scale. The beauty quark, with its asymmetrical decay, is the key that unlocks this next grand chapter. Our maps will be redrawn, our textbooks rewritten, but the intrinsic, meditative beauty of the cosmos remains completely unchanged. Let us embrace this uncertainty not with fear, but with the joyful humility of a child encountering the vast ocean for the very first time, knowing that the journey of discovery is the true destination. Have you ever held a piece of glass marveling at its smooth surface, only to place it under a microscope and discover a landscape of jagged peaks and deep valleys? Our human minds crave order, We construct elegant buildings with straight lines. We divide our days into exact hours, and we expect the universe to behave with the same predictable symmetry. We want the cosmos to be a flawless mirror, reflecting our own logic back to us. But the deeper we gaze into the quantum realm, the more we realize that perfection is a human illusion. The universe does not build with straight lines. It builds with probabilities, chaotic energy, and broken symmetries. The discovery deep within the Large Hadron Collider, where the beauty quark refuses to follow the balanced rules of our mathematical models, is a testament to this wild, untamed nature of reality. It is a quiet rebellion against our desire for pristine order, revealing a cosmos that is infinitely more complex and beautiful than a simple, perfect mirror. The anomaly challenges our fundamental belief in a balanced cosmos. Before we explore the profound philosophical meaning of this broken mirror, I want to pause our journey for a moment. I am Theodore, the researcher, your companion on this path through the endless mysteries of the cosmos. I have noticed that 71% of the curious souls who watch these videos and share in this peaceful exploration have not yet subscribed to the channel. If you find comfort, wonder, and intellectual safety in our shared contemplation of the universe, please take a moment to subscribe. It helps our quiet community grow, allowing us to continue unraveling the vast tapestry of existence together, and it ensures that we can keep exploring these deep questions as a family of cosmic learners. Now, let us return to the shattered symmetry of the quantum world and discover why a broken rule might be the greatest gift the universe has ever given us. For generations, theoretical physicists pursued the dream of a grand unified theory. They sought a single, elegant equation that could explain every particle and every force in the universe, a mathematical poem of absolute symmetry. They believed that at the beginning of time, in the blazing heat of the Big Bang, all forces were one, united in a state of flawless equilibrium. As the universe expanded and cooled, this pristine unity shattered, breaking into the distinct forces we experience today. Gravity pulling the stars, electromagnetism lighting the dark, and the nuclear forces binding the atoms. We mapped this shattered landscape with the Standard Model, finding incredible beauty in the surviving patterns. Lepton flavor universality was one of those enduring patterns, a comforting assurance that the universe still maintained a sense of fairness among its fundamental particles. We believed the electron and the muon received absolute equality from the weak nuclear force. When the researchers at CERN observed the beauty quark decaying into electrons more often than muons, they found a profound flaw in our assumption of cosmic fairness. The universe, in its ancient silence, is showing a preference. To a human mind demanding order, this preference feels like a mistake. But in the grand architecture of the cosmos, there are no mistakes. Every anomaly, every broken rule, is a doorway leading to a deeper layer of truth. If the weak nuclear force plays favorites, it suggests the presence of a hidden hand, a new physics operating behind the scenes. This hidden hand might belong to a new particle, a heavy messenger carrying unknown rules from the dark sector of reality. Or it might indicate that our visible universe is interacting with hidden dimensions of space, realms where the rules of our Standard Model hold no power. The cosmos is vast, and our maps trace only the shores of a boundless ocean. Consider the sheer audacity of our endeavor. We are biological organisms, born on a tiny rocky planet orbiting an unremarkable star in a galaxy containing hundreds of billions of other stars. We are composed of the very same quantum fields we are trying to understand. Yet, we build subterranean rings spanning 27 kilometers, chill them to near absolute zero, and smash protons together at speeds rivaling light itself, all to read the encrypted language of creation. When the universe replies with a paradox, when it presents an anomaly like the decay of the beauty quark, it teaches us the ultimate lesson in cosmic humility. It reminds us that our human logic is a product of evolution designed for survival, not a universal key guaranteed to unlock all the secrets of existence. We must approach the quantum world not as conquerors demanding answers, but as humble students listening to an ancient, infinite teacher. To grasp the scale of our ignorance is to experience a profound sense of awe. The visible matter in the universe, everything we can see, touch, and measure, constitutes a mere 5% of the total cosmos. The rest is divided between dark matter, the invisible scaffolding holding the galaxies together, and dark energy, the mysterious force accelerating the expansion of space itself. The Standard Model, our crowning intellectual achievement, explains only that tiny 5%. It is a map of the bright islands, ignoring the vast, dark ocean that surrounds them. The anomaly of the beauty quark is a ripple arriving from that dark ocean. It is the first tangible sign that the physics of the dark sector is brushing against the physics of our visible world. The hypothetical Z-prime boson, or the elusive leptoquark, might be the long-sought bridge connecting these two vast realms, allowing us to glimpse the underlying unity of the entire cosmos. Consider the concept of time in this grand exploration. When we look up at the night sky, we are looking into the past. The light from a distant star takes billions of years to cross the dark expanse and reach our eyes. We see the universe not as it is, but as it was in ancient epochs. The physics experiments at CERN perform a similar feat, but instead of looking across vast distances, they look back in time to the very beginning. The collisions inside the Large Hadron Collider recreate the fierce energy of the newborn universe. In tracing the decay of the beauty quark, physicists act as historians of the first milliseconds of creation. They read the ancient scrolls written in particle tracks and energy spikes. Finding an anomaly in these records is equivalent to finding a forgotten chapter in the history of the cosmos. It implies the universe had a different character in its infancy, a character dominated by unknown particles and asymmetric forces that laid the foundation for the matter we see today. The vastness of time and the microscopic scale of quantum fields merge into a single, breathtaking narrative of origin and destiny. This pursuit of knowledge is not a cold, sterile exercise in mathematics. It is an emotional, spiritual journey. When we realize that the atoms in our bodies were forged in the hearts of dying stars, and that the quantum fields giving us mass are the same fields guiding the ancient galaxies, we feel a profound connection to the whole of existence. We are not separate from the universe. We are the universe observing itself. The famous astronomer Carl Sagan expressed this truth with striking clarity, reminding us that we are a way for the cosmos to know itself. But the anomaly at CERN takes this connection further. It tells us that we are made of star stuff governed by rules we do not yet comprehend. Our very existence might depend on the broken symmetries and the hidden particles currently whispering in the data streams of the Large Hadron Collider. The silence of space is filled with these unseen forces, binding us to the furthest reaches of the infinite void. We exist in a delicate balance between the infinite vastness of the cosmos and the infinitesimal complexity of the quantum realm. Our human scale sits in the middle of these two extremes. We can touch a tree, build a fire, and chart the phases of the moon. Yet, our minds possess the unparalleled ability to journey inward to the scale of quarks and outward to the edge of the observable universe. The tension between the known and the unknown generates a productive intellectual energy. When a rule breaks, like the apparent violation of Lepton flavor universality, it shatters our complacency. It forces us to ask new questions. What if the universe contains entire continents of physics we have never imagined? What if the empty space around us pulses with energies we cannot feel? The anomaly is an invitation to step out of our comfortable certainty and venture into the dark woods of the unknown. Science transforms ignorance into motivation. Every unanswered question is a promise of future discovery, a reason to keep building machines, writing equations, and looking into the dark. The path forward requires immense patience. The researchers will continue to collect data, sifting through billions of microscopic collisions to confirm or refute the anomaly. They will build larger, more sensitive machines, pushing the boundaries of engineering to capture the faintest echoes of the quantum realm. Whether the current anomaly climbs to the golden standard of 5 standard deviations or dissolves into statistical noise, the quest will endure. The human spirit thrives on mystery. We are explorers standing on the shores of an infinite cosmic ocean, staring into the dark, knowing that the greatest discoveries still lie ahead. Every broken rule, every unexpected paradox, is a beacon guiding us toward a more unified understanding of reality. We do not fear the unknown. We embrace it as the source of all wonder and awe. As you navigate the familiar routines of your daily life, take a moment to reflect on the invisible, humming reality that underpins your existence. The solid ground beneath your feet, the air filling your lungs, and the light warming your skin are all manifestations of ancient, dynamic quantum fields. Beneath the calm surface of your perception, a microscopic universe is engaged in a restless, infinite dance. The anomaly of the beauty quark is a reminder that this dance is not a predictable waltz, but a complex, evolving choreography filled with unexpected turns and hidden dimensions. We live in a cosmos that is vast, wild, and fundamentally mysterious. To accept this mystery is to find peace. We do not need to possess all the answers to appreciate the breathtaking beauty of the question. Let us continue to wander through this infinite museum of wonders, our minds open to the paradoxes, our hearts filled with awe, and our eyes forever turned toward the quiet, infinite dark. The journey itself is our destination, a path of infinite learning stretching out among the ancient stars. Have you ever sat beneath a canopy of ancient stars, feeling the weight of the infinite night pressing down, and realize that you are a vital part of that vastness? We journey through life seeking answers, hoping to build a fortress of certainty around our minds. We gather facts, construct theories, and weave elegant equations to explain the grand dance of the cosmos. Yet, the universe possesses a beautiful, unyielding wildness. It resists our attempts to box it into simple paradigms. The discovery at the European Organization for Nuclear Research, the subtle anomaly found within the shattered fragments of the beauty quark, is the universe showing us its wild heart. It is a profound reminder that reality is not a solved equation, but a living, breathing mystery. When the weak nuclear force shows a preference for the electron over the massive moon, it shatters our expectation of cosmic symmetry. It breaks the pristine mirror of the standard model, not to plunge us into chaos, but to invite us into a deeper, more profound layer of understanding. The anomaly is a threshold. It is the beginning of a new era of exploration, one that will redefine our place within the infinite silence. Before we take our final steps together in this exploration of the quantum realm, I want to pause for a quiet moment of reflection. I am Theodore, the researcher, your companion on this path of cosmic discovery. I have observed that 71% of the curious souls who walk this meditative journey with us have not yet subscribed to the channel. if you find peace, intellectual safety, and a sense of wonder in our shared contemplation of the universe, please take a gentle moment to subscribe. It helps our quiet community grow, ensuring we can continue unraveling the vast tapestry of existence together as a family of learners. Now, let us return to the threshold of the unknown and embrace the magnificent poetry of an imperfect universe. The human drive to explore is a fundamental force of nature. It is as elemental as gravity or electromagnetism. We are compelled to look beyond the horizon, to sail across uncharted oceans, and to build massive subterranean machines to map the invisible architecture of matter. When we look at the Large Hadron Collider, we see a ring of superconducting magnets spanning 27 kilometers, a marvel of engineering cooled to temperatures near absolute zero. But we also see a monument to human hope. It is a cathedral of curiosity, built by thousands of minds working in harmony to read the ancient text of the cosmos. The data flowing from these silent, colossal detectors is a river of numbers, a digital echo of the Big Bang. And within that river, the anomaly of the beauty quark is a golden grain of sand. It is a tiny, unexpected discrepancy that carries the weight of a revolution. Physicists do not view this broken symmetry with despair. They view it with profound excitement. A flawless theory gives us comfort, but a broken theory gives us progress. It tells us where to look next. Imagine the universe as a vast, ancient forest. For centuries, we have walked along a well-worn path, cataloging the trees, observing the flora, and learning the behavior of the creatures we can see. The Standard Model is our map of this path. It is brilliant, detailed, and useful. But the Anomaly is a glowing footprint leading off the path and into the deep, dark woods. It suggests the existence of hidden realms, perhaps the dark sector where unseen particles weave the invisible scaffolding of the galaxies, or perhaps higher dimensions where gravity and quantum mechanics merge into a single, beautiful truth. The hypothetical heavy messenger particles, the entities that might cause the beauty quark to decay with an asymmetrical bias, are the native inhabitants of those deep woods. They interact with our visible world through the faintest whispers, leaving delicate traces in the data that require years of patient analysis to decipher. Carl Sagan once reflected on our place in the cosmos, noting that we are a way for the universe to know itself. This thought transforms our perspective from passive observers to active participants in the grand cosmic drama. The atoms composing your hands, your heart, and your mind were forged in the stellar furnaces of ancient stars that lived and died billions of years ago. The quantum fields granting those atoms mass are the same fields vibrating throughout the infinite void of space. You are an intricate, walking collection of the universe's most fundamental components, organized by billions of years of evolution into a being capable of asking questions about its own origins. When you contemplate the anomaly of the beauty quark, you are star stuff contemplating the deepest mysteries of its own construction, the tension between the visible and the invisible, the known and the unknown, is the engine of our intellectual evolution. The beauty of science lies not in final answers, but in the infinite journey of questioning. The quest to resolve the anomaly of Lepton flavor universality will span decades. It will require the construction of new colliders, the development of more sensitive detectors, and the birth of new physical theories that we cannot yet imagine. Some might find this endless pursuit exhausting, a sign that human knowledge is forever incomplete. But there is a profound meditative peace found in the acceptance of mystery. The universe is not a puzzle meant to be finished and put away on a shelf. It is a vast, unfolding reality that invites continuous engagement. When we accept that we will never know everything, we free ourselves to marvel at the things we do know and to look forward to the things we have yet to discover. The quiet cosmos is a museum of infinite wonders, and we have unlimited time to explore its halls. Let us consider the scale of the physical world. At the microscopic level, particles pop in and out of existence in a frantic, probabilistic dance. At the macroscopic level, galaxies merge over billions of years in a slow, silent ballet governed by gravity and dark matter. Our human lives exist in the delicate middle ground between these extremes. We experience the flow of time in minutes, hours, and years. We measure space in meters and kilometers. Yet, our consciousness bridges the gap. We can calculate the decay rate of a beauty quark, living for a trillionth of a second, and we can project the trajectory of a galaxy cluster spanning tens of millions of light years. This capacity for abstract thought is our greatest gift. It allows us to hold the entire universe in our minds, to appreciate its beauty, and to recognize our intimate connection to its ancient processes. The Anomaly at the European Organization for Nuclear Research is a reminder that the universe does not owe us simplicity. It does not exist to satisfy our desire for neat mathematical resolutions. The cosmos is wild, asymmetrical, and filled with shadows. The preference for electrons over moons in the decay of a specific subatomic particle might seem like an obscure detail, but it is a thread pulling at the fabric of reality. If we follow that thread, it might lead us to a complete understanding of dark matter, the mysterious substance outweighing visible matter 5-1. It might lead us to a unified theory of quantum gravity, bridging the gap between the monumental theories of Albert Einstein and the microscopic world of quantum mechanics. Or it might lead us to a truth even more bizarre and wonderful, a concept we currently lack the language to describe. The unknown is not an empty void. It is a space filled with potential. As we draw this journey to a close, I invite you to carry this sense of wonder with you. When you look at a tree, a stone, or a fellow human being, remember that beneath the surface of the visible world lies a humming, dynamic network of quantum fields. The solidity of the objects around you is an illusion created by the interaction of invisible forces. The symmetry we perceive is only a local phenomenon, a calm eddy in a vast, turbulent, cosmic river. The universe is a place of profound complexity, built on rules that we are still struggling to translate. But the struggle is beautiful. The attempt to understand, the collective effort of thousands of minds working across generations to decode the ancient silence, is the most noble pursuit of our species. We are explorers, armed with curiosity and mathematics, navigating an ocean of starlight and dark energy. There is no final destination in this exploration. Every time we answer a question, the universe presents us with two more. The anomaly of the beauty quark will eventually be resolved, either confirmed as a new law of nature or explained by an unseen interaction within the current model. But by the time that happens, we will have discovered new anomalies, new paradoxes, and new mysteries to keep us moving forward. The learning is an infinite journey, and in that journey, we find our purpose. We find peace in the act of looking into the dark and asking what lies beyond the shadows. We find a sense of community with every other curious mind that has ever looked up at the stars and wondered. The universe is vast, ancient, and filled with quiet magic. Thank you for sharing this quiet space of contemplation with me. Our exploration of the quantum realm and the broken symmetries of nature has reached a resting point, but the path of discovery continues forever. If this exploration brought you a sense of cosmic peace and a renewed appreciation for the mysteries that surround us, please share your thoughts. What other quiet corners of the cosmos shall we explore next? Your curiosity guides our journey, and If you wish to remain a part of this community of cosmic explorers, please subscribe to the channel, ensuring we can walk together into the beautiful, infinite unknown. Keep your mind open, your heart full of wonder, and your eyes looking toward the endless night